Dear students, welcome to today's practical class in which we are going to learn how to perform the diffraction grating experiment in our laboratory. The aim of the experiment is to determine the wavelength of different spectral lines in the mercury spectrum using diffraction by grating minimum deviation method. The apparatus required: spectrometer, grating, mercury vapor lamp, magnifying lens, spirit level. Now we will have a look on the different parts of a spectrometer. This one is collimator. This provides the bright and sharp image of the slit. This one is telescope to observe the spectral lines. And this is the eyepiece. And this is the rack pinion setup to focus the telescope. And this is the prism table. And this is the grating holder. And this is the transparent window through which we can observe the spectrometer reading, through which we can see the main scale and vernier scale. This is the main scale and this is the vernier scale. Now we are going to measure the least count of the spectrometer. What is the meaning of least count? How much minimum value we can measure accurately by using this instrument. The formula for least count is 1 main scale division by number of vernier scale divisions. How to measure this 1 MSD value? If you take this main scale here from 170 to 180, 10 degrees. And if you observe how many divisions made between 170 to 180, if you see how many divisions are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, another 10, 20 divisions. So 10 degrees are divided into 20 divisions. So therefore 20 divisions equal to 10 degree. Then 1 division equal to 10 by 20 degree, that equal to half degree. We know 1 degree equal to 60 minutes, therefore half degree equal to 30 minutes. So 1 main scale division equal to 0.5 degree or 30 minutes. Then this is the vernier scale, that is from 0 to 30. How many divisions are there on the vernier scale? 30 divisions. So number of vernier scale divisions are 30. So therefore, least count equal to 30 minutes by 30, that equal to 1 minute. That means we can measure accurately 1 by 60th part of a degree by using this spectrometer. Now we'll have a look on how to measure the reading. So the spectrometer reading equal to main scale reading plus vernier coincide into least count. How we can measure the main scale reading? To measure the main scale reading, the process is we have to know the value of, on the main scale before 0 of the vernier scale. Before 0, this is the 0 of vernier. Before 0 of vernier, what is the value on the main scale? So this is the value is 170 and we know 1 division equal to 0.5 degree. Therefore, the value on the main scale is 170.5 degree. So the main scale reading equal to 170.5 degree. Then vernier coincide. Out of these 30 vernier divisions, 1 division is exactly coincide with the main scale. So if you observe this one, this is not coincide here, this is not coincide, this is not like this. If you observe, so this one is exactly coincide. So what is the vernier coincide value? 0, 5, 10, 15, 20, 21, 22. So the vernier coincide value is 22. So multiply the vernier coincide with least count. So 22 into 1 minute and convert into degree. That is converted by divide the value with 60 because we know 1 degree equals 60 minutes. So the value is equal to 0.37 degree. Therefore, the spectrometer reading equal to main scale reading 170.5 plus 0.37, that equal to 170.87 degree. Now we will have a look on the different screws attached to the spectrometer. What is the role of? And if you observe this screw, If you tighten this screw, spectrometer will not move. Sorry, telescope will not move. If you release the screw, then telescope will move freely. Okay. If you tighten the screw, telescope will not move. Then if you want to move it in small angles, then we can use this screw. This is the fine adjustment. This will work only when the previous screw what I have shown that has tightened. Then you can move this one in small angles. Then coming to this another screw here, if this one is tightened, then this will not move. If you release this screw, then this will move. That means the vernier scale attached to this one also will move. If you tighten this one, this will not move. At the situation, if you want to rotate at small angle, then you use this screw. That is for fine adjustment. Then if you rotate this one, it will move at small angles. Then this screw used to increase the width of the slit. If you tighten the screw, then this width will increase. If you release the screw, then this width will decrease. If the width is very high, we didn't get sharp spectrum. That's why we have to minimize the width of slit. If width of slit is very less, then we don't get bright spectral lines. So we have to optimize the width of slit in between brightness of this spectral line and sharpness of the spectral line. Now we have to make the three principal adjustments of the spectrometer before using the spectrometer for experiment purpose. Those are first one is eyepiece adjustment. This is the eyepiece of the telescope. If you observe, focus the telescope to whitewashed wall and observe through this eyepiece, then you will get you will observe the two lines, vertical wire and horizontal wire. These are called cross wires. If the crosswires image is blurred, so we can't measure the reading accurately. So the crosswires image must be very clear. So for that we have to adjust this eyepiece. If we adjust this eyepiece by focusing the telescope to whitewash wall and move this eyepiece until the crosswires are very clear and sharp. Okay, so through observe through this one and adjust until the crosswires are very clear and sharp. When the crosswires are also very clear, stop moving the eyepiece. Then second adjustment you have to make is focus the telescope to distant object. Focus the telescope to distant object and adjust the rack pinion adjustment until the distant object observe very clear. So this is the rack pinion adjustment and adjust this one until the image is observed very clear. Once the image is very clear, then stop moving of the rack pinion setup. Then next adjustment is you have to make the present table horizontal. For that purpose, we are using spirit level. And below this present table, we are having the screw. Adjust this screw until the air bubble observed here that comes at center of these lines. After making these primary adjustment, then take the spectrometer to mercury vapor lamp, switch on the mercury vapor lamp, focus the collimator to the mercury vapor lamp, and observe the slit image through the telescope. If slit image is slit width is very high, then we have to adjust the screw until width of the slit is coming to the required value. We have to adjust this one until the width of the slit comes to the required. So width of the slit is okay. Then we have to focus this image until we are getting a sharp image of the slit by adjusting this rack pin attachment to the collimator. So once the slit image is very clear, then put the vertical crosshair on the slit image. Then the collimator, telescope both are in the same line. Note down the reading. That reading is direct reading. So this is the direct reading. Then put the grating in the grating holder. Before keeping the grating in the grating holder, you have to know what is the grating. Grating is nothing but an arrangement of large number of slits which are having equal width and equal opaque space. What is the grating? An arrangement of large number of slits which are having equal width and equal opaque space. How will design a grating? Generally, we are taking a glass plate on which we are drawing a line by using a fine diamond point. The drawn line is opaque to the light. The gap between lines acts as a slit. So this is the slit and this is the opaque place. In this way, we have to draw number of lines on the grating. If you observe our laboratory grating here, if you observe here, so here 15,000 LPA, that means 15,000 lines per inch. So on this grating, 15,000 lines per inch is drawn. So now we have to focus the light onto the grating. Then from other side, if you observe, we can get the spatter lines. This is the light beam we are getting from the collimator that is focused onto the grating. Other side, we are keeping the telescope, through which telescope we can observe the spatter lines. If the collimator and telescope both are on the same line, then we will get the slit image only, that is the zero order diffraction spectrum. And if you move the telescope either left or right, we can observe the spatter lines. When you are moving from the straight position, the first set of spatter lines we are observing, that is the first order spectrum. Again, if you move further, then we can get the another set of spatter lines, those are second order spectrum. For present experiment, we are working with the first order spectrum only. And before going to this one, I want to tell you what is the phenomena taking place. When the light is instant here, the diffraction of light is taking place. What is the diffraction? Bending of light waves at the corners of sharp obstacles or narrow slits is known as diffraction. There are two kinds of diffractions are there. Fraunhofer diffraction, in which the source and screen both are at effective infinity. Second one is Fresnel diffraction, in which the source and screen are at a finite distance. In the present experiment, the kind of diffraction we are using is Fraunhofer diffraction. Now, keep the grating in the grating holder. Then move the telescope either left or right until you are observing the spatter lines. So if you move like this, first you will get blue line, first you will get violet, sorry, first you will get violet, next blue, next gray, and next yellow one, yellow two. After observing these spatter lines, we have to put the grating in the minimum deviation position. What is the minimum deviation position here? If you rotate the grating, then these spatter lines also move like this. At a particular position, they will come back. If you rotate the grating reverse direction, then spatter lines are moving like this and going there. Suppose if you rotate grating like this, and these spatter lines are moves like this. If you rotate the grating reverse, then these spatter lines are moving like this. So at what position they are moving back, that position is called minimum deviation position. That's why we have to rotate the grating up to this position where they are moving back. That position is called minimum deviation position. So now we have to rotate the grating up to such a position where the spatter lines are moving back. That position is called minimum deviation position. So now rotate the grating here slowly. until the position reaches where the spec lines are moving. Once they are reaching that position, stop the rotation of grating. So now we kept the grating in the minimum deviation position. Then focus the telescope and put the vertical crosshair on the violet color. Note down the reading. Then again move the telescope to second color and keep it on the blue color and note down the reading. Again note down the another reading by keeping the vertical crosshair on the green like that yellow one and yellow to tabulate the values. So this is the table for keep the values what you are observing in the spectrometer diffraction grating experiment. So here for first violet color, note on the main scale reading and what the vernier coincident and multiply this vernier coincident with least count, that is 9 minutes, divide with 60 converted degree and add to main scale reading, that equal to 36.65. Like that blue, either green, and that yellow one, yellow two, and this is the flat reading that we are observing in the starting of the experiment. And if you observe this yellow one, yellow two, they are very near to each other. Sometimes there is only change in the vernier coincident only. Now we have to find out the angle of minimum deviation. For that we have to subtract all these minimum deviation, all these values observed, spectrometer readings, subtract from the direct reading. That means 36.65 minus 25.18. That will give the angle of minimum deviation of violet. Again, 37.72 minus 25.18. This one, like that you can. So then you will get the angle of minimum deviation for all these spectral lines, what we are observed. Then put this value of D here, then we can measure the wavelength of the spectral lines. The formula we are using here is lambda equal to 2c sine D by 2 by n angstrom unit. Here lambda is the wavelength of the spectral line, c is the grating constant, D is the angle of minimum deviation. That means these values. And n is the order of the spectrum. In the starting of the experiment, we already discussed n equal to 1. So n equal to 1 and D is the angle of minimum deviation. These are the angle of minimum deviation values. So we can measure lambda by knowing the value of grating constant. So for measuring this grating constant, we are using this angle of minimum deviation value correspond to green color that we have considered as a theta z. Please remember that we are using to measure the value of c. So here c equal to lambda g by 2 sine theta z by 2. That value already has shown in the previous slide, that is 15.70, and lambda g equal to 5461 angstrom unit. So substitute these values, 5461 by 2 sine 15.70 by 2, that equal to 19,991.93 angstrom units. This is the value of grating constant, and substitute this value of c here and d values from this column here, and we can get the wavelength of the spectral lines of different colors. Violet is this much, and blue is this much, and green is this much. Like this. So thank you for listening. And I think you can understand, you can easily perform the same experiment in the laboratory by using the our setups. Thank you.